Hi, welcome back to the course Data Science by RouteFabric. And today, let us learn about supervised learning. In the previous videos, we have learned what machine learning is and the concept of supervised learning. Now let us make a small deep dive into supervised learning. As you may recall, we said that the input variables are X, which are the feature vectors of a supervised learning model, and the labels are Y. Now let us look at the errors versus the complexity in supervised learning. Usually in supervised learning, we split the data set in a 80-20 split. Sometimes we also do 70-30 split for a good amount in training and testing data. As the complexity increases, the training error decreases. But as the complexity increases, the chance of overfitting error increases as well. The generalization error, which is the test error, usually has a parabolic expression where in the center of complexity, or where the training error and the overfitting error are same, that's where the local maximum of the testing error exists. This is usually the point where we consider a good model, or where we consider the error to be good and the complexity to be good. Now let us look at the two main types of supervised learning: classification and regression. Classification has a discrete label as the output, whereas regression has a continuous value as the output. Now let us take an example and work through some classification and regression problems. Let's take an example of waiting for a table at a restaurant, and the following are its given attributes. Now this is how a training set will look. The attributes are your X values and the target, which is your Y, output labels. Now let us use the decision tree example for the will you wait for a table in a restaurant. If the restaurant is empty, you don't need to wait, so you exit out of the decision tree. The next is that if you have some space in the restaurant, this is when you will wait for your table for them to clean and get it ready. The next step is when the restaurant is fully packed, you will ask for estimate time to wait. Now you go into the subsection of the decision tree. Now we see if the wait is greater than 60 minutes, is it between 30 to 60 minutes, is it between 10 to 30 minutes, or is it between 10 minutes, or 0 to 10 minutes. If it's greater than 60 minutes, according to the data, you will not stay at the restaurant, you will now wait for your table. If it's between 30 to 60 minutes, then you go into another big tree. But if the time is between 0 to 10 minutes, you will wait and you will wait for your table. And we go till the end. Now choosing the attributes for your decision tree. Unlike hard coding the rule base to see what happens, the decision tree is automatically generated by the machine learning model based on the data. A good rule of thumb to choosing the attributes, or where the attributes are assigned, is to keep all the positive on one side and all the negative on the other side. This helps us create less noisy models. Now let us look at what information gain is. Information gain is the concept that decides how the decision tree is morphed, or how the decision tree is made. The main takeaway is the formula, which is the gain of A is equal to B times the probability divided by probability plus not the probability minus the remainder of A. Now let us look at the smaller version of the decision tree. Is the restaurant empty? If the restaurant is empty, there is no need to wait. If the restaurant is half full or partially full, you have to wait for them to create your table. If the restaurant is full, are you hungry or are you not? If you're not hungry, you can leave, or you will not wait. If you are hungry, then depending on the type of cuisine, you will decide whether you want to wait. Now, overfitting is a concept that happens in machine learning models. You can overfit a model and get a false accuracy of your model, or false prediction, because of the data. And in decision tree, to avoid the concept of overfitting, all you got to do is prune the decision tree, eliminate nodes that are not clearly relevant. We look at the test node that has only leaf nodes as descendants. If the test appears to be not useful to the decision tree, with the information gain close to 0, then we eliminate the test, or we eliminate that branch. We repeat this process and consider each test, which is with only leaf descendants, until each one has either been pruned or accepted as is. Now let's look at what entropy is. Entropy is, in the simplest terms, is nothing but the measure of disorder, or the check to see how much purity or impurity is in your system. Entropy is the error of the model. Now let's look at Naïve Bayes. Naïve Bayes is a classification model which can be used to find email spam. It is a classification technique based on Bayes' theorem with an assumption of independence among predictors, which are your feature selections of X values. In simple terms, a Naïve Bayes classifier assumes that the presence of all particular features in a class is unrelated to the presence of any other features. Now let's consider an example. A fruit may be considered to be an apple if it's red, round, and about 3 inches in diameter. Even if these features depend on each other or upon the existence of other features, all of these properties are considered independently. So when Naïve Bayes is classifying a brand new data set or brand new data entry, it'll see if it's red. If it's red, it sets points into if it's an apple. If it's round, it increases the probability for something to be an apple. If it's about 3 inches in diameter, it increases the odds of it becoming an apple. Similar to the Bayes theorem, the Naïve Bayes formula is that the posterior probability is equal to the likelihood times the class prior probability divided by the predictor prior probability. Example of Naïve Bayes is the spam detection. Spam detection is really useful detection for email because there are a lot of spams that enter your email. In the example, we can see some of the spams are wholesale fashion watches minus 50% today, designer watches for cheap. The way that Naïve Bayes or any spam detection works is that you create bag of words. Bag of words only counts the frequency of the occurrence of the words. If there is high frequency of occurrence of the words such as cheap, 57% today, dollar, money, unbeatable price, or capitalization of words, then we say that it has a high frequency of those words to be a spam. Now let us see an example of spam and non-harmful email. A spam is offer a secret, click secret link, secret sport link. And non-harm is a play sport today, went play sport, secret sport, event sport is today, sport costs money. The size of the vocabulary is 12. And the probability E is equal to spam for a random email E is 3 by 8. Now let us look at inference. We already learned about statistical inference, and now let us see how to use it. The input is prior distribution of spam or ham, which is probability of spam or probability of ham. And the likelihood, which is probability of word given spam and probability of word given ham for any word W. The output is the posterior, which is the probability of spam given X, which is a bag of X is equal to a bag of words. And now we are going to integrate everything into an Naïve Bayes network for it to learn faster. Now, how many parameters at most are required for Bayes network with 12 words in the dictionary? 1 for prior, which is probability of either spam or ham. 11 parameters for spam likelihood, which is probability of word given spam. And 11 for ham likelihood, which is probability of word given ham. So overall, we need 23 parameters at most for Bayes network with 12 words in the dictionary. Now let us look at an example where we apply the bag of words and find the probability of it being spam or ham. For the example, we have the spam email, which is offer is secret, click secret link, secret sport link, sport money sport. And for the ham email, we have play sport today, went play sport, secret sport event, sport is today, sport costs money. Now let's consider the word sport. For the probability of it being spam, it's 3/8 because it occurred 3 times in the spam, and the total occurrences of sport is 8 times in the whole data. Probability of ham is 5/8. because it appeared five times in the ham email. Now the probability of word given spam is 1/3 or 3/9 because there are 9 words in the spam email and 3 of them are sport. And the probability of word given ham is 1/3 as well because the amount of words in ham is 15 and the amount of times sport occurred is 5 times. Now let us compute the probability spam given word. To find the probability of spam given word, it is probability of word given spam times probability of spam divided by probability of word given spam times probability of spam plus the probability word given spam times probability of ham. After we compute this, we find the probability of spam given word is 1/18th. So the word is not a spam and we add it to the bag of words. Now let us look at the limitations of Naïve Bayes network. The bag of words has a strong independency assumption. If there is no strong independency assumption, the performance of Naïve Bayes is severely affected. The other features could be utilized to improve the accuracy. Even though there is no strong independence assumption, the other features could be utilized to improve the accuracy of the Naïve Bayes network. Now let us look at how we can reduce the chance of overfitting in a Naïve Bayes network. We can use Laplace smoothing, which is helpful to reduce overfitting in Naïve Bayes. We can also do a change in how we are splitting the data. Instead of doing an 80-20 split, we can do 80-10-10, where 10% of the data goes into cross-validation to adjust the k-value. Now let us look at some supervised learning examples. First, we have the regression. A regression model is one of the techniques in supervised learning which draws a line based on the data which best fits the information. Now let us see what's a reasonable price for a 2,500 square feet house. We can see that as we go up here to the line, we can see that a 2,500 square feet house has a price of around 800K. The way that the regression model finds it is with the hedge function. The hedge of x is equal to 0.237x plus 246. The 0.232 and 246 are the bias that are created by the model. And for a house of x is equal to 2,500, we get that the value of the house is around 826,000. Now let us look at a small introduction to logistic regression. Logistic regression is one of the classification models and where the hedge of x function is between 0 or 1. Logistic regression is also one of a soft classification because the probability is between 0 and 1. Supervised learning is split into two other branches, which is parametric and non-parametric. Some examples in the parametric are decision tree, Naïve Bayes network, linear regression, logistic regression, and in the non-parametrics we have SVM and k-nearest neighbors. Now let us see what a SVM is. First, let's see which one is the best separator out of two classes of data. We can see that the red one is far better than the orange one. Now let us see what a support vector machine is. The goal of a support vector machine is to maximize the margin separator to yield better clustering or classification results. A support vector machine is used as a supervised learning. Now, how do we find the separator? Similarly, how we discussed in unsupervised learning for k-means, we keep changing the separator in a way that maximizes the space between the marginal separators until we get the best marginal separator. Now let us look at what k-nearest neighbors mean. K-nearest neighbors is similar to k-means clustering, but k-nearest neighbors is a supervised learning, where a data point is classified by a majority word of its neighbors. If k is equal to 1, then the data point is simply assigned to the class of the single nearest neighbor. If k is equal to 5, the data point is assigned to a class of the 5 nearest neighbors. The algorithm needs to memorize all data, so if the data is huge, it requires a lot of processing power. And now let us see a quick example on how k nearest neighbor works. And now let us see with the example k is equal to 1. The obvious choice of A is it'll be positive or plus sign. For B, it'll be positive sign because positive is really close to B. For C, it is negative. Even if the k is increased to 3, the chance that B is gonna change to negative is not there because the closest 3 points to B are all positive. Now let us look at how leftlet smoothing helps, or a smoothing parameter where we keep increasing the k values. The first image we are looking at is k is equal to 1. That means the data point is decided to be in a particular category of the same or of the given labels, deciding on the single nearest neighbor. Now if we increase it to 3, we can see that it's much smoother. If we increase it to 5, it's even smoother, and you can see that the line has a clear cut of where the two labels are identified. The problems with k-nearest neighbor is that very large datasets usually make it hard for k-nearest neighbors to work because it needs to memorize all the data. And if it has large feature spaces, it cannot process it because it takes too much space to memorize and too much power to process. I hope this was informative. To learn more about data science, please visit RouteFabric.com. Thank you and have a nice day.